rehabilitation. And
Yes.
expert of the session is Dr. Amit Konar. Dr. Konar will share his diversified knowledge on the topic for an hour. And after that, for the last half an hour, we will have interactive session or question answer session. Before Dr. Konar start the session, let me introduce him. Professor Konar is a researcher and professor in electronics and telecommunication engineering department, Jadavpur University, with a H index of 50 and Google Scholar citation over 1400. Professor Konar earned his B in electronics and telecommunication from Indian Institute of Engineering Science and Technology in 1983. Dr. Konar earned his ME in Control Engineering in 1985, MPhil in System Modeling in 1988, and PhD in Artificial Intelligence in 1994, all from Jadavpur University. Professor Konar is author of 15 books, including two popular texts, Artificial Intelligence and Soft Computing. The second one is Behavioral and Cognitive Modeling of Human Brain. Dr. Konar published 35 peer-reviewed book chapters and over 100 research papers in leading international journals. Over 350 research papers have been published in IEEE flagship conference. Professor Konar supervised 29 PhD theses, over 400 master theses in the area of AI and robotics and cognitive neuroscience. Professor Konar delivered speech in top flagship IEEE conference, including WCCI 2020 and ICA SSP 2016. Dr. Konar is serving as associate editor of IEEE TFS and IEEE TETCI for several years. He is currently the EIC of the Springer book series on cognitive intelligence and robotics. He also served as coordinator and principal investigator of several national level projects funded by Government of India and industry. His current research interest includes cognitive neuroscience, type 2 fuzzy logic, multi-agent systems, and scientific creativity. Now I will request Professor Konar to start the session. Over to you, sir.
Thank you so much. Thank you, Professor Kapil Dev, for introducing myself. I am thankful to Professor Rupa Bhattacharyya for inviting me to this program. I am really very, very happy to be a part of this program, ATAL program on FDP for medical technology challenges and opportunities under the Make in India framework. So I am thankful to all organizers of the FIEM, and also I am thankful to the participants for joining my session. So I just briefly outline in this session what is brain-computer interfacing and how this can be utilized for neuromotor rehabilitation of people suffering from neuromotor diseases. Okay, so this is basically a particularly topic that fits well within the medical technology challenges under Make in India framework. And because we developed the same thing over last 10 years at Jadavpur University in Artificial Intelligence Lab. Okay, so I am just giving the presentation of the topic. The title is Brain-Computer Interface for Neuromotor Rehabilitation. Next slide. Next slide. Just a minute. Yes. Now, for any research, the first thing is you have to finalize your target. Okay. So, Professor Kapil Dev, can you hear me? It's okay?
Yes, sir. Yes, sir. You are
Okay, okay,
clearly
fine.
audible. Please
Okay, okay,
continue.
thank you. And you can also change you can find the slide changes.
Yes, sir. Yes, sir.
Okay,
Clearly
okay, fine.
visible.
Okay. If any problem, please point out. So for
Okay,
any
sir.
research, there is a targeted objective. Our final and targeted objective is ultimately to place a particular integrated circuit, one IC, in the brain of people who are suffering from neuromotor disabilities. I mean, by placing this, we want to make that person, mobile in case he is unable to move his arms, maybe particularly forearms. So can we place an IC properly designed in the brain so that he can move his arms properly so as to do any kind of physical task which he is now unable to do because of neural problem, neuromotor disability. Okay. But ultimately that is the objective, but we could not reach that objective till this date. This is just a mission, or you can say vision, but ultimately we could do very little of the work, and what we have done that I will be presenting in this session. Now, let me tell you what is basically brain-computer interface. In any brain-computer interface, you must have at least one computer and one human brain. Now, why I say single computer, if we have multiple computers, then that is also possible, but we need to have at least one computer, which will generate some stimulus for the brain. The stimulus can be of different types, could be a video or audio stimulus, could be any kind of touch sensation, so tactile stimulus, or it could be any kind of aromatic stimuli like olfactory stimulus. So anything that can stimulate the human brain of a normal or maybe person suffering from neuromotor disability. So whenever you provide some stimulus by a computer or by any other automation that may not be always computer, could be any other automation that can generate tactile or olfactory stimuli. And then brain effectively, if it can respond to that, it will generate certain kind of signals, maybe electrical signals, or could be some kind of brain images. So those signals and images are the reflection what the brain is doing. When the stimuli or stimulus is actually submitted to the brain. So those signals or those images are captured and transferred back to the computer. In case there are multiple computer, one could be the stimulus generation and other could be for analysis. If you have a single computer that does both the job of stimuli generation and feedback signal reception and analysis of those feedback signals or images. Now, effectively, there is one very famous professor, Olpa, who is also a neuromotor surgeon. According to him, brain-computer interfacing means it's a non-muscular or artificial channel of communication between a human brain and a computer. So now the question is, this must be artificial channel. These arrows are artificial channels, not like normal neuromuscular channels. Next thing is, why do we go for BCI? The common objective I already pointed out in the first slide, that ultimately we want to design a chip integrated circuit that has to be placed in the brain. So that is the final targeted objective. But in brief, what is BCI? Because we could not attain that thing. We actually want to recognize the brain states from the brain signals. If the brain is stimulated by some signal, maybe some video, the brain is stimulated then the stimulated response of the brain, the signals or images, if we capture by some automation, by some machines, and if we analyze that by a computer, can we say what the brain is doing now? So that means we can recognize the brain state. We can also control the brain state if we know from one brain state, if by submission of certain stimulus to the brain, it is moves to another brain state. Then we have a large number of instances of the input brain state to the final brain state and the state transitions required by the stimulus. So if you have a long list, then we can ultimately control the brain state from, say, for example, when a person is relaxed, I can make the person happy or I can make the person sad. So this is the emotional state transition diagram. So if I can recognize the brain state from the brain response, say for happiness, I can recognize from brain response, or sadness, I can recognize from brain response. Relaxation of the brain, if I recognize from the brain response. And if I do plenty of experiments to generate certain music or video to make changes in the brain state from relaxed to say happy or relaxed to sadness, then the question is I can keep track or record of them, that what are the stimuli I need to provide at the relaxed state to make the brain happy or to make the brain sad. Then if we have those recording, then effectively we can control the brain state or control the state transition in the brain states by suitably selected control signals. So this is basically the second motivation of brain-computer interface. This not only is restricted to emotional signal transition, it could be representing any kind of cognitive processes in the brain like motor control, maybe any perceptual process, and many other processes, in fact, all possible processes that the brain have, and that we can model and that we can actually recognize the brain states, and the state transition in the brain can be controlled by identifying the necessary inputs for state transition for the brain. Now, the next thing is how actually brain model the our thoughts into electrical signals, how the brain transforms our thoughts into electrical signals. Suppose a person is having a visual stimulus. There may be something on the stimulator board or in a computer screen, and the person is observing that visual stimulus. During observation, he has two kinds of thoughts. One may be his memory bound. He may have some past incidents which he finds has coincidence with the stimulus here, or this stimulus could be completely new. So he may have some kind of new feeling or sensations, maybe emotions, maybe perception, maybe any kind of new learning. It could be any kind of motor actions, as it is mentioned, move your left hand or right hand kind. So it could be any kind of stimulus provided in the visual stimuli documentation. And on just seeing this, the person automatically generates some, generate some actually positive and negative, small amplitude charges separated by a very small distance. Okay. And these basically, are called electrically, they are called dipoles. So because they are basically very small charges of same amplitude, same magnitude, positive and negative charges separated by a very small segment. Now the question is, these dipoles automatically and naturally are created inside a particular tissue, or you can call it cell, that they are basically, hanging from the brain, and inside that there is positive charges, outside that negative charges are created, and those cells are commonly referred to as pyramidal cells. So in the pyramidal cell, inside positive and outside negative charges and their concentration, they are being actually governed by the input stimulus. Now, if you have any electrode placed on the scalp, then according to Coulomb's law, you will be getting some potential at that point because of charges inside the locality of the brain. So we know the Coulomb's law from our high school background. So effectively, more is the distance of the charge, less is the effect of the potential at this point on the scalp, and more the charges are closer, they have a bigger effect on the potential at that point. So if we have number of electrodes placed on the brain, everywhere we will be getting some electrical potential. Now, what happens when the charges are accumulated? Sometimes the charges they rest there, and sometimes no, because of that electric field may vanish when the input stimulus vanishes, or that charges may be influenced by any secondary thoughts as well, and effectively there may be disbalances or imbalances or changes in the charges, which causes effectively some change of potential at any point. So over time, if we see as the input stimulus is changing, there may be change in potential. When the person is having a secondary thought, but input stimulus is static, he may have a change in potential at any point on the scalp. So effectively, we are getting an electrical signal varying with time. Those electrical signals are captured by EEG machine and then transferred to some computer after some processing to decode what the brain is doing right now, whether the brain states can be controlled by the visual or any other kind of stimulus. Now here actually I briefly outline electroencephalography or EEG process, because in my presentation today we'll be discussing on EEG based classification and motor control. Although we have another instrument, functional near infrared spectroscopy, but in one presentation covering both will be too difficult for audience. So suppose this is an EEG acquisition machine, and they are basically sensors, basically they are electrodes looking like small buttons. And those button-like electrodes are placed over the surface of the scalp. And when the person is having any kind of cognitive thoughts from the memory or observing or having any kind of stimulation, then effectively, as I pointed out, he is liberating charges inside the brain, and for that he'll be having electrical signals at any point on the skull. So we'll be getting those electrical signals by EEG acquisition machine, amplify each signal by 60 to 100 times, and then we just have a electrical low pass filter to filter the signal between 0.1 to 100 hertz. Sometimes some signal may have a higher frequency, but we want to keep it within 0.1 to 100 hertz, because beyond that, most of the electrical signals generated by the brain are having a cutoff frequency of 100 hertz. So if we have different channels, for example, in the diagram, I have considered 7 channels. We must have 7 such channels, CH1 to CH7. Although written 3, we must have 7 such channels, and from each channel, we'll be getting time varying signals. X-axis is time, and Y-axis is actually signal in millivolts. Now, after we get the EEG signal from the EEG machine, so the yellow diagram, this part of the diagram is inside the EEG machine, which nothing you have to do except to place electrode on the skull. So you can ask the person to have a EEG cap placed on his head, and automatically or maybe you can have directly, you can connect the electrodes on the skull by some manual process. Both processes are active. And once you do that, you can get the EEG signal from here. And then for specific cognitive tasks, you need to process it. For example, if you ask someone to move his left hand or right hand, and suppose the person is a normal, healthy person, then when he moves his left hand, he'll be generating some electrical signal from the right part of his brain. So this is his left hand. He's liberating signal from the right part of his brain, right part of motor cortex. When he's moving his right hand, he'll be generating signal from the left part of his motor cortex. This signal is specific wave shape of V type that I will explain later, and that has a frequency spectrum from 2 to 18 hertz. So although the original input signal has frequency spectra 0.1 to 100 hertz for motor control, for left hand or right hand movement, when the brain signals are liberated, you need to again filter it in a narrower band between 2 to 18 hertz, which is subset of the original band 0.1 to 100 hertz. Similarly, for other cognitive tasks, for example, for visual perception or audio perception or linguistic perception, means language understanding, or motor control, or maybe audio control, there are different frequency bands which are subset of the original frequency band. So you need to put another band pass filter between of specific frequency band as required. And then from the signals, you have to extract certain features. So up to this, there is electronics. And from here onwards, you have computer science. So when you extract the features, you can use different techniques. Like you can use modern techniques like convolution neural network. You can use traditional techniques of feature extraction, like say time series plotting. From that, you can get some features. So there are plenty of techniques of feature extraction in statistical pattern recognition technique you can use. And after we extract the features, you need to put a classifier to classify the brain states. For example, if there are 3 possible tasks, suppose a person may be asked to do either left hand movement, you command the person, you think of moving your left arm, or you ask the person to move his right hand, or you do not say the person to do anything. So there are 3 possible classes: left hand movement or right hand movement imagination, or no movement imagination. So in that case, there are 3 classes: one for left hand movement imagination, other is right hand movement imagination, or no movement imagination. And these 3 can be classified by any typical classifier like support vector machine or CNN or any other standard classifier you can employ, which will classify the features extracted from the brain into any of the 3 classes. Only one class will be active. Suppose the left hand motor imagination, a subject was asked to move his left hand in his mind. So even if he has hand or he does not have hand, he can think of left hand motor imagination, and automatically from the right part of the motor cortex, brain signal will be liberated, the V type of signal, and here the left hand motor imagination input of the controller will be active, other 2 inputs will be passive, will not be active. Since this is active, the controller, then what the controller has to do, it has to move the robot arm, maybe the bottommost arm called waist arm, counterclockwise. It is a counterclockwise movement shown by arrow, so it will start moving counterclockwise. In case the person was asked to move right hand motor imagination, suppose second link is for right hand motor imagination, that is classified by the classifier, then if right hand motor imagination is active, the robot, this say bottom arm which is called waist control, now we move clockwise. So opposite direction as shown here, opposite to this. So in that way, you can control the robot arm, by generating appropriate control commands for the robot arm to move this individual link of the robot. This is called the waist link. This is called this a shoulder link because this looks like shoulder point junction, and this is elbow junction. So elbow link, lower limb of the person. So in that way, you can have the control of the three links of the robot arm, and also you can control the gripper by your mind control brain signal. Now the question is, so this is in brief the overall thing, how actually from brain signal you can effectively control a robot arm to serve the purpose that you think of. That means if the person in the stimulus it is written, just think of moving your left arm. The person thinks of moving his left hand, and from the effectively from brain signal you extracted features, you classified the left hand motor imagination, feed it to the controller, and automatically the robot starts moving counterclockwise. The whole process I just briefly outlined in this slide, but this is not so easy. In fact, if you need to do research, there are a lot many scope to do research. One is you can go for signal processing, electronics engineers or electrical engineers can do this thing well. You can go for feature extraction where a computer scientist can do. You can go for classifier design, you can again a computer scientist can do, and controller design, then is somebody of electronics or electrical engineering may have to take help from computer scientists to jointly serve the purpose. Okay, so this is in brief the overall scope of research in this domain. Let me now focus on the individual aspects, how EEG signal actually can be processed, can be captured, can be processed, and what are the inner meanings of the EEG signals as you capture from the brain. Is there any kind of physical interpretation of a specific signal that we look for right now? Now, I just first discuss, there are actually 10 different types of, the commonly called event-related potentials. Event-related potential means when you generate some brain signal within few seconds of time or few milliseconds of time, we understand that the brain signal is generated and we can capture the brain signal. That means I submit stimulus to the person, and after submission of this stimulus within few milliseconds time, maybe the brain will generate the specific signal. They are called time-locked signals, and they are also called event-related potential, ERPs. Now I will be discussing, there are 10 to 12 different ERPs. Now I discuss only 2 ERPs, and using these two, I just demonstrate how can you develop a machine that can be controlled, that a robot arm that can be controlled by your thought. Then gradually I will move step by step by presenting other brain signals, and within the time as many as I can discuss. But right now I discuss only 2 brain signals. One is called ERD, event related desynchronization, followed by event related synchronization, ERD, ERS. Now, suppose whenever a person thinks of any hand movement, suppose he's thinking to move his right hand, then from the left part of his motor cortex, it is called left hand motor imagination. So from the left part of the motor cortex, he is releasing this V kind of signal. When the person thinks of moving his, say, left hand, then from the right part of his motor cortex, he will be liberating this V kind of signal. So this is called motor imagination signal. In all case, it looks like a V. Now, question is why it looks like a V. When the person thinks of moving his left hand, automatically more negative charges are assembled in the just below the cortex, in the left side of the cortex. So when the person is thinking to moving his right hand, in the left part of his cortex, there are more negative charges. So the signal amplitude gradually decreases on the surface by Coulomb's law, because there are more negative charges just below the skull. But when the thought is removed, when he is no more thinking of motor imagination, MI for motor imagination. Suppose he stopped motor imagination here, then automatically the negative charges are abolished. Negative and positive charges, they actually collide and combine, and there will be chargelessness, and gradually the signal will be as usual. What resting signal was there, it will be gradually coming to the resting signal value as it had before, the V type of signal. So effectively signal amplitude grows after the subject stops motor imagination. So during thought of any kind of left hand or right hand motor imagination, LHMI or RHMI, the signal actually starts falling off, and when motor imagination stops, it gradually grows. So effectively you get a V kind of signal, and this signature actually indicates the person was thinking either to move his left hand or move his right hand. Even if he really moves his left hand or right hand, the signal amplitude will be bigger. But in both cases, whether he thinks to move or whether he really moves, in both cases you'll be getting this V type of signal. The other signal is called error-related potential. Whenever, suppose you just discovered that you committed any error, any kind of error, for example, you were just moving on a corridor very fast, supposed to take your class. You all of you are faculty here, so you are moving very fast to take your class. And suddenly there is a bending, 90-degree bending, and an old professor was moving, coming towards you. You did not see him, you just collided him, he fell down. And then you say, alas, what happened? The old professor fell down. As you thought like this, you generated the error signal, and because of his movement, movement related error, you will be generating the error related potential signal from the time point when you discover you committed any error. And the signal is looking like this: first negative, then again small positive, and again small negative. So this is the signature of the signal error related potential. And this happens when you find any other person or even yourself, you committed error, or other person committed error, or even a robot or a machine committed any error. It will be ERRP signal will be released from your brain. This signal is released from the midline of your brain as shown by red line. And anywhere on the midline of the brain, if you place electrode, you will be getting this negative, then small positive, again small negative signal. Now, using these two signal, motor imagination and ERRP signal, we will design a machine first. Let me show you how to design a machine using these two. Suppose there is a circular arc, as you see. Over the circular arc, there is a timber, as you find. The timber is connected. Timber is just like a stick or a pointer. And this is connected with a motor. Motor is perpendicular to this plane of the screen. Suppose there is a motor perpendicular to the screen. So as the motor turns, this particular pointer or the timber also moves over the circular rim. Do you understand? So initially circular rim is here at the stop position. As the motor is turned, this timber or the pointer moves over the circular rim, and it has to stop here. And you need to control this thing automatically by your brain. How actually you can control this thing automatically by your brain, that I will be discussing now. So what you do, I will be using only two signals: motor imagination signal and error related potential signal. How? Actually, what I mean, so whenever the person wants to move the motor, suppose somebody on the screen writes, you think of moving your right hand. So right hand motor imagination written on the screen. And the subject or the experimental subject, who is a person, a normal or healthy person, he just watches on the screen, it is given right hand motor imagination. Then he thinks of moving his right hand. As he thinks of moving his right hand, you have a feature extraction from the brain. Brain signals are captured by EEG machine, then features are extracted and fed to classifier. The classifier has three outcomes, as I pointed out: either right hand movement or left hand movement or no movement. And the classifier correctly says, yes, it is right hand movement. So as the classifier correctly says it is right hand movement, there is a program which then controls which just connects to the motor to actually move the stick from the stop point towards the target position. So the stick started moving. That means what happens? When the person thinks of moving his right hand, automatically you can think, automatically stick starts moving. But in between there are three processes to extract the signals from the brain of right hand motor imagination, then feature extraction from the signal, and also classification into right hand motor imagination or left hand motor imagination or no signal. In this case, it was right hand motor imagination. So by sensing this, you are feeding a control command to the robot arm or to the motor to start moving, and the stick started moving. Stick continues moving, but once the stick has to stop here. So you are watching that you are the subject. You are watching that stick is continuously moving. Once the stick attains this position, then you have to think that it has to be stopped. But once it attains this position, Nothing will happen. As it attempts to cross the position, just cross the position, you think, alas, what has happened? The stick has crossed the target point, so an error has occurred. As you think like this, an error-related potential signal, as I pointed out, will be generated from the brain, as you have done from the midline of the brain. The negative followed by positive followed by negative signal. And then that has to be fetched, that has to be acquired by the EEG machine, that has to be features from the signal is to be extracted and fed to the classifier. When the classifier will say any of the two possibility, is it an error ERRP signal or it is not an ERRP signal? If it is an ERRP signal, means error related potential signal, then you generate a control command by another program to this motor, the stop the motor. But the motor has crossed the target point, so you can stop it, but after some small error, because the motor will stop here as it already crossed the target point. So what you need to do? In order to bring it back, if you do the experiment 100 times, and in each case you see how much is the offshoot, how much is the offshoot or overshoot from this position, you take the average value of the overshoot for 100 experimental trials, and you just move it back by program control, the average by the average value, so it will come to the target position. So this is our first experiment we have done around 12 years ago from now in Artificial Intelligence Lab, Jadavpur University. I just now, what happened? It is not moving. Okay, okay. So next is, the same thing, same person is actually controlling the robot arm from the start point to the stop point. But what happens on the signal? Just see, this is the time axis, x-axis is time in all cases. So the subject has liberated motor imagination signal first. So this is the motor imagination V type of signal. As he stopped imagining motor imagination signal, the motor started moving. So motor is on from this point onwards. Motor will be on. How long will be on? Motor will be on until this pointer comes to the stop point. So the pointer, when it comes to the stop point here, the person has to make it off. As it crosses the stop point, the person has to make it off. So the person will release the ERRP signal at this time point. So this is the ERRP signal, negative, positive, then negative. So by getting the ERRP signal and by classifying this into ERRP, we can switch off the motor. So the motor is made off now. So as you made the motor off somewhat here, effectively you will be getting, the input signal. This is actually actual desired position is theta d angle and current position is theta c. So when theta c is actually equal to theta d, you need to stop. But by that time it has crossed some position. So there is an overshoot here, this much overshoot. This is called steady state error, SSE. Why overshoot? Because the person had stopped it after the link crossed the target point when error occurred. So there is an overshoot. This is the overshoot amplitude, and this is called steady state error. To avoid steady state error, as I told you, you have to take average value of steady state error for 100 experimental trials on the same person and turn the motor back from this position, final position, back to the stop point by moving back by the average value of the steady state error. Now, what is involved here? This is the thing that we have done. But how computer science and electronics, how they are using here? Just see. Basically, just look at from the person's point of view, the subject's point of view. Subject actually initially, there is a PowerPoint presentation for the subject who is being trained. Initially, he has to be trained. If you put a subject on screen, he cannot follow anything. He cannot be participating properly. So you need to do some experiment on the person at least for 1 week before you really ask him to participate formally. So what you need to do, there is a PowerPoint screen with 4 basically PowerPoint presentation slides. In the first slide, there is a fixation cross for 2 seconds. You have a big cross. Ask the person to look at the fixation cross to put your full concentration on the screen for 2 seconds. This is an attentive phase when the person is fully attentive and on the screen. Then in the next, there is written on the screen, try to think of moving your right arm. Just think, not move. The person will think of moving his right arm. This is right hand motor imagination. 3 seconds are given for this. Why? Because within the 3 seconds, the person will think of right hand motor imagination. And within that time, that signal will be fetched from the brain. Then that is actually features will be extracted and classified to be right hand motor imagination. That means the BCI system has to understand that the subject is thinking of right hand motor imagination. So you need to allow some time of 3 seconds. And after the person completed right hand motor imagination, he is waiting. Why is he waiting? He is waiting whether the link crosses the target stop point. So he has to wait until it crosses just crosses the stop point. And when it crosses the stop point, he will say in his mind, alas, what has happened? And immediately the ERRP signal will be released from the midline of his brain. So he is waiting for the ERRP to be released, and ERRP will be ultimately released, and within the 2-second time, he has to decode that it is ERRP, whether error occurred or error did not occur. If error has occurred, what to do? You have to turn the stick back to its previous position because there is overshoot. Okay, you have to stop the stick movement and turn it back by a small overshoot. Okay, so these are the process the subject is doing. They are the time called time windowing. Now, in the system, what is being done? In the system, first you have to do motor imagination pre-processing. That means when the subject thinks of right hand motor imagination, you have to pre-process the signal. And then motor imagination feature extraction. You have to extract certain features from the right hand motor imagery signal and classify the signal. Classify to what? Classify whether it is a right hand motor imagination or left hand motor imagination or no motor imagination. What is it? If it is right hand motor imagination, then you then command the motor. This is the motor. This is the motor. Start the motor clock counterclockwise. So motor will start moving counterclockwise. After the motors, when the motor actually carrying the stick crosses the target point, as I already pointed out, as the motor crosses the stop point here, then what will happen? You have to stop the stick. How to stop? So you have to detect ERRP, because by that time, as the motor crosses the target point, you'll be releasing the ERRP signal from the midline of the brain, as you find here, the ERRP signal. And then what to do? Then actually you need to stop. But how to stop? Will you stop? How the BCI system will stop the motor? That is philosophically fine. You have to stop the motor. But how to stop the motor? For that, first the system has to decode the ERP signal. That means the EEG signal from your brain has to be acquired like this. EEG signal is acquired from your brain, ERP signal. And after acquisition, you have to pass through 2 steps. One is basically pre-processing of the signal. That means filtering of the signal in the desired band, then feature extraction from the signal, and classification of the signal. Classification into whether ERRP occurred or ERRP did not occur. Only 2 classes. And if one of the class is active, suppose if it is ERRP occurred means actually that ERRP occurred means the target position has been crossed by the stick here, then you need to stop the motor. So what to do in hardware? Then if ERRP occurs, then you stop the motor and turn it back by an offset. Why turn it back? Because the stick is now here. So you have to turn it by an average offset value of 100 previous experimental trials. So basically that thing is, if ERRP occurs, stop the motor and turn back by a fixed offset angle. So this is basically the thing. In the actual algorithm, what you do, you have to look for 2 things. Did the person think of motor imagination? Can you detect the motor imagination? First thing, can you detect right hand motor imagination? If you did not detect it, that means the person could not generate right hand motor imagination, or there is a failure in a system which fails to classify right hand motor imagination even if subject imagined right hand motor imagination. So nothing to do. Only in case subject has currently has done the right hand motor imagination, and also your system could correctly detect the right hand motor imagination, then you exit this question mark box. If yes, then it is right hand motor imagination was currently done by the subject and that was detected by the classifier correctly here. Then what to do? Then you command the robot to start moving. So robot now starts moving from this point. Now what happens then? Then you are waiting for ERRP. Did the robot arm, did this stick cross the target point, stop point? If no, you are waiting. You are waiting for the error-related potential to occur, that the subject or the person will liberate from his brain. How long will you wait? For 2 cases. If the subject could correctly generate the ERRP signal, that will make him practice over 7 days. Whether he can correctly generate ERRP signal at the right time point when error really occurred, that means the stick has crossed the target point, stop point. And in case the subject can correctly generate the ERRP signal and your BCI system classifier could correctly classify the ERRP signal, that means here, yes, ERRP could be classified to be correct. Then you come here. Then what? then stop the motor and turn it back by a fixed offset angle that I already pointed out. The stick was here, you turn it back by a fixed offset angle, which is average of previous 100 experimental trials. So this is the very basic scheme that we developed long ago, around 12 years ago, but first in our country and also internationally, after say, after only one country, Austria. Austria is a very good worker, Professor Seller. He did it long back ago, around 15 years ago, and we did this thing in Jadavpur University 12 years ago, and nationally first, before all IITs and ISC. Now, this was very elementary thing that we developed. Then we modified this thing. Why modification? It was done for a single link robot arm. Single link means it can has only one link of a robot arm by a motor. This cannot be practicable for in three-dimensional system or two-dimensional system. This won't work. So what we need to do now? We have to do it. We have to implement the same thing on 2D planning or three-dimensional planning. Here is an example of 2D planning. Suppose this is a robot arm. OARB is a robot arm. These are the different, this is called, entire thing is the robot arm, and these are called link. This is link one. OA is one link, like our waist. This is like our waist. Our body, if we just stand erect, stands vertically, then OA is our waist, body representing. And we can turn around our waist, so we can turn around OA, in this direction, perpendicular to this plane. Then this is AR, means our shoulder here. This R is basically our elbow. And this is a move. There are other links I do not discuss. There is an end effector or gripper that can grip a ball, and the ball is placed on a stick. Suppose ball is placed on the stick and the entire robot arm is also in the plane OQW. That means ball and the robot arm entirely lie on the same plane. But the problem is that the link RS is below the ball. It is not, it is almost it has come to the ball. Suppose it is just below the ball. In this position, it cannot grip the ball. So what the person has to do? The person has to do two steps. One is motor imagination and error-related potential. When RS is much below this line, suppose RS is here. Just think of RS is here. And the person thinks of moving it up. How? There is a motor and the person thinks of right-hand motor imagination. As he thinks of right-hand motor imagination, this link RS will gradually move up on the plane. On the plane OQW, it gradually moves up. As it crosses the line RB, you will find what happened. My alas, what has happened? The line RS has crossed the line RB. So now the ball could not be reached, ball could not be gripped. And immediately the person will generate the error-related potential, ERRP signal. So the motor has to be stopped. This motor connected to the link, as I shown here, to move up, that has to be stopped and then turn back to the fixed offset by a fixed offset angle, as I did for previous case after experimenting this 100 times. And the average of the 100 angular movements you have to compute and to turn it back. So what will happen? RS link is moved up by motor imagination, and as it crosses the target line RB, you have to turn it back, you have to stop it and turn it back by sensing the ERRP signal. These are the main steps written here. So this is how to control on a plane. Now, if it is 3D, then it is a more complex problem. Suppose the ball is in a different plane OQW and the robot arm is in a plane OPW. This is the robot arm OARS, and this is end effector or gripper. This is lying in the plane OPW and ball is lying in the plane OQW. Ball is lying on a stand here. This is a stand. What to do now? Here is a subject who will think of right-hand motor imagination. As the subject thinks of right-hand motor imagination, the entire robot arm OARS lying on the plane OPW will start moving clockwise. Just see from top, if you see, this is clockwise movement, the blue arrow, clockwise movement. From top, if you see, it is clockwise movement. Just look at your watch, it is clockwise. So the entire robot arm OARS lying in the plane OPW, containing plane OPW, whole thing will start moving. How long? Why is it moving? Because person thinks of right-hand motor imagination, whose objective is to move the robot arm around the axis OA. So as the entire robot arm OARS is moving with the plane OPW, one time point will come when it crosses the target plane OQW. Because ball is there. We need to catch the ball by the, we need to pick up the ball by the gripper S. So what will happen as OPW plane crosses OQW? Suppose it is here. Then the person says, alas, what has happened? The plane OPW carrying the robot arm crosses the target plane OQW. So there is an error occurred. and as the person thinks of the error, automatically will liberating ERRP signal from the midline of his brain, and that signal is sensed by the EEG machine, captured by EEG machine, filtered, features are extracted and fed to a classifier very fast, already done, hardware is already ready, and after classification it says yes, and ERRP has occurred. What is the meaning of the ERRP? The meaning is only nothing but OPW plane has crossed the target plane OQW. So now the robot is commanded to stop. Hardware is already ready. When the plane OPW will cross that plane OQW, the ERRP will be released by the person and not decoding the ERRP by a classifier. The classifier says the robot has to be stopped right now. So the movement of the robot around the Y axis is now stopped. But by this time, the robot is in OPW plane is here crossing OQW. So it has to turn back. How much it has to be turned back so that it can come to the plane OQW once again? To get it again, you need to experiment 100 times, and for each time we'll getting some angular error between OPW here in new position OP-W say and OQW, and the angular error is averaged, and then you turn it back by the average angular error, and then OPW plane now coincides with OQW. So what we did, again here we did one cycle of motor imagination to start moving the entire robot containing plane OPW around way, and when it crossed the target plane OQW, the plane of the ball, we have to stop it. So by ERRP signal. So again using motor imagination and ERRP signal, we could stop this. After this robot arm is in the plane OQW, the situation could be like this, which we already discussed, and then actually you need to move up RS link towards RB to hit to actually grip this ball. That is similar with the previous thing that we discussed. So what we learned so far, that if I have an object at one position just here, we require a target point is a position here, is a fixed position. If the object is on a plane, as you find here, the object is in a plane, the ball is in a plane where the robot is lying, then the target is a line, not a point. Target is a line RB. And in the next slide, what you find, when the object is in a different plane, OQW, apart from the plane of the robot arm, which is in the plane OPW, then actually I need to move 3D movement. So target is a plane. So the target could be a point, as I already pointed out, target could be a point here. The target in one-dimensional position control, target could be a point. In two-dimensional position control, the target could be a line RB. In three-dimensional position control, target could be a plane OQW, OPW to OQW. So the subject has to be taught this thing, and after many experiments, he can do that thing. Now, this is the overall thing that if we could first publish in 2017, in international IEEE transaction, but we had other papers in top conference and Elsevier journals before, because we started sometimes in 2000, 2010, 11, like that, and approximately more than 12 years. So what happens here? In this case, the same thing. I have for 3 link robot arm we have done. For each link, there is a link classifier. This is a link classifier, which says clockwise movement of the link or counterclockwise movement of a link or no movement of the link. And these signals can the classifier are activated by some features. Inputs are features and outputs are any of the 3 classes for the classifier. But in this case, there is a problem. The problem is initially when we did experiment, we could not communicate to the robot which link we need to active right now. Which link should it move? Should it the link 1 OA or link 2 AR or the link 3 RS? So always we have to start with link 1, then link 2, then link 3. In case the link 1 and link 2 need not be moved, still we have to allow some wait cycle, because we could not communicate to the robot by brain-computer interface which link we need to command. That we could do after publication of that paper. I pointed out this paper in 2017. And then an idea came in our mind. We can communicate individual link to control. That I will discuss later. So what is happening from some electrodes in the motor cortex? These are the electrode number. We extracted feature and we can first select link 1. This is link 1. And we can control link 1 by motor imagination and error-related potential, only using these 2 signals, which is our innovation, first type our innovation internationally. I mean, Preferred Seller also did not do that thing. He has done on open loop system using only motor imagination. He did not use ERRP signal for a feedback control. From the feedback control point of view, our work is internationally first. So then you need to use link 1 first to classify its clockwise movement, or counterclockwise movement or no movement. After the movement of this link is over, we go for link 2's classification. If we require, then we need to move it clockwise, counterclockwise, or no movement kind. In that way, for 3 link, we can do. But for each link, after the link started moving, we need to actually get the ERRP signal. So this is for motor imagery signal followed by ERRP signal. After the link has moved and the target plane has, for example, this is link has started moving, but the target plane OPW could not cross OQW. Link is moving still. So, but when the OPW crosses OQW, you are generating ERRP signal, but that has to be decoded. So we have to extract features from ERRP signal, and then we need to classify ERRP as error or no error. If it is error, then the motor has to be stopped. Motor has started moving previously from this plane OPW towards OQW. If error occurs, means OPW crossed OQW, you need to stop the motor. As you need to stop the motor, you command the motor driver to stop the corresponding link's motor. But this way, for individual link, we did this thing. Now I show you the whole thing in a video demonstration. So this is an experimental subject. This is our EEG machine. This is the Jacko robot arm. The robot arm has to pick up a ball and place it in a basket. These are the EEG signal captured from the brain of the subject. These are electrodes placed on the skull. There are 2 reference electrodes, one left and right here. And these are electrodes like placed on the skull. So brain signals are captured by EEG machine, and then they are decoded by the EEG computer. The classifier is there, and then the classified signal is transferred to a robot computer, where the robot actually controls the individual link movement, and as the person thinks, the robot will move accordingly. I mean, right hand motor imagination, robot has to move, follow 2 steps, either motor imagination and ERRP signal. Just see the video now. So these are the signals captured from the brain. You can see the V type of signals, which are easily can be seen. They are actually motor imagery signal. Other signals you cannot see because they have very tiny magnitude. You can only get them after signal processing and classification. But motor imagery signal are very big, you can see it. Now the robot has to think to move this link 1 so that it can reach the plane of the ball. But it has crossed the plane of the ball. So error occurred, so it has to turn back. It has turned back. Now this link has to come to the ball link, RS. It has gone down, but it has crossed the target line. So error occurred, it is moving up. Now these 2 fingers need to be horizontal. But it is been horizontal, but there is small error. So needs to be corrected and correction done. Now the person think of twice right hand motor imagination, which means grip. So it is gripped. Now she wants to move it up by 45 degree. But it has more than 45 degree. So there is an error and she corrects it by thinking. Now the entire robot arm has to move towards the plane of the box. But it has crossed the plane of the box. So error occurred and she thought of moving it back. Now this link has to go down towards the ball. So this is the line. But it has crossed the line. So it is corrected. Now she thinks twice left hand motor imagination, which means release the ball. So ball is released. So entire thing is done by the subject's brain, and this was our first experimental setup which was published in IEEE in that paper. Now I show you the next thing, what are modifications. So what are the results? Now we have used a classifier. For this classification, we have used different techniques. Particularly, we have used support vector machine that gives best result that will show in the next slide. And these are different motor imagination are classified. And also, positional error is classified. Their positional error decoder means this is positional error classification. Accuracy is high, both for motor imagery and positional error. Positional error has more classification accuracy. Computational time is 0.152 second per command. The steady state error is here 3%. Peak overshoot means how much is crossing the target point for 4.6%. And for entire robot commanding to pick up the ball and place, it requires 56 seconds. Now, these are different techniques that we use. One is if we use features at Zort parameters and power spectral density and use backpropagation classifier, then we require training time 22 minutes and accuracy is 78.6%. But best result is given by ZORT parameters and power spectral density, and classifier is support vector machines. Training time is 8 minutes and classification accuracy is very high. But that work has some limitations. The limitations are corrected in these two papers. What are the limitations? It is fixed order link selection. That means always I need to select link 1, then link 2, then link 3 in order. Even if link 1 need not be moved, link 2 need not be moved, only link 3's movement is good enough, still I have to allow some wait cycles for link 1's movement and link 2's movement, which is simply wastage of time. But why so? The idea is we did not know how to communicate robots link that you do automatically, not electrically, but by thoughts. How can we control, how can we communicate to link 1 of the robot? You move now. That we could not do, so you have to follow some sequence. And now we modified this. But how? I just point out here. So that is called fixed order link selection is the limitation. Now we can do random order link selection. Any order, link 1, link 2, link 3, whichever is required, you can select that link in random order. I will show how. Second, actually, there is a large steady state error. Why large steady state error? Because you see when the target position is crossed by the robot arm, say in one dimensional case, when the target position stop point is being crossed by that, then only subject generates error. If the subject is slow, he may take a lot of time, maybe say for example 0.1 second to generate the error after the robotic link crossed the stop point. So during the 0.1 second, if the speed of the motor is high, it has crossed a large amount. So there is a big overshoot, and you see the overshoot. This is desired angle of motion, and this is actual angle that crossed the target line, this desired value. So there is a large steady state error that has to be removed. How can we remove that? If we can allow oscillation around this and stop, just like suppose there is a 400-meter race and you have to stop at the target point. Normally, we did not ask the person to stop at the target point. But if the policy is that you have to stop at the target point, then the runners know, the sports person, if he crosses the target point with high speed, he has to come back. Then, but even if again crosses down, he cannot stop. He has to oscillate and stop. But if we have to implement this thing, then we must have to do some other brain signal, that is P300 signal, to handle this process, which we did not discuss yet, but we can discuss it right now. So basically, I need to discuss 2 points. How, if there is a steady state error, how to overcome, and if there is fixed order link selection, we can make it random order link selection. These 2 points are covered in these 2 papers. Now, what is now new brain signal, P300? So because first implementation is over, now I'm going for more advanced implementation, but not difficult. You can easily understand this. This is the brain. This is the parietal lobe of the brain, which is very, very useful for smart planning operation. When you swim or when you dance or when you move your hand movement control for gesture control like a policeman or anybody else, then actually the parietal lobe is used for smart planning. Any kind of sport, any kinds of fielding in cricket, you need to have a smarter control of your limbs, because otherwise you cannot catch. As you see the international say women's tournament few days ago. So how beautiful was the catch, when one person, when one lady actually, she jumps towards the ball with entire body movement and gradually moves her leg to bring it down. But that was at a high altitude. How this could be done? By a very smart body control, and this is done by the parietal lobe of the brain. That is very important function of the parietal lobe. It generates one signal P300. I give you an example. When does it generate P300? Suppose you are listening to your favorite music. So brain is generating some rhythmic signal like this. At one sudden point, after what happens here at this time point, suddenly you hear a bombasting sound coming from outside. Very big bombasting sound. Then you forget, you forget to, just listen to your music. Your attention entirely shifts to bombasting sound. And immediately from this time point, after 300 milliseconds, you will be generating a very large amplitude signal from parietal lobe. This signal is called P300 signal because there is a positive deflection of the signal from the brain after 300 milliseconds from here to here on the stimulus of the oddball signal. Oddball signal means that boom signal, that is an oddball signal that disturbs listening your music. So from that point of the boom signal, you will be getting after 300 milliseconds a large peak, and that is called P300 signal. We use this P300 signal and other signal here. The second signal that we'll be using is steady state visual evoked potential, SSVP. What is this? Suppose on a TV screen, you are seeing a flickering signal. Flickering means glowing, say, on and off kind of signal. Okay, if you see that kind of signal and that has a frequency, suppose frequency is 6 Hz, then in frequency domain, there is a large peak in the signal. If you pick up the signal from the occipital lobe, this is occipital lobe is opposite to your eye in the back side of your brain. So if you pick up the signal, steady state visual evoked potential, SSBP from an EEG electrode, you will be finding the signal at a peak with a peak of 6 Hz. If x-axis is frequency, not time, and y-axis is amplitude. We have used this signal to eliminate the problem of fixed order link selection. But how? Just see. Suppose this is one robot arm, and with each robotic link, we have one light emitting diode. Light emitting diode or LEDs. All of us know LEDs nowadays. LED lamp everywhere. During our Deepavali, we often use LED lamps. You know, they are glittering. They are actually on and off. So basically, as they get on and off, there is a frequency. I have put a red LED with 8 Hz frequency here, a green LED with 12 Hz frequency, and a blue LED with 16 Hz frequency, 8, 12, 16. Do we have to fix it only 8, 12, 16? No, they must be distinct. So the person actually wants to communicate link 1. It is your turn, link 1. It is your turn now. How does the person communicate? He simply has to look at the link 1, which is flickering with the red LED at 8 Hz. As he looks at this arm, 8 Hz signal will be coming up from his occipital lobe, SSBP signal. And the EEG machine and the EEG machine captures the signal, transfers to the BCI system, which classifies, yes, it is 8 Hz SSBP. But 8 Hz SSBP means it is link 1. So BCI system then understands the subject wants to communicate link 1. It wants to carry a message for link 1. What message? That it is the turn of link 1 to move right now for right hand motor imagination. If the subject, instead of looking at link 1, looks at link 3 at 6, which is blinking at 16 Hz, then automatically 16 Hz signal will be coming up from the occipital lobe, a peak with 16 Hz. And the BCI system, after signal processing, feature extraction, and classifying, understands that it is an SSBP signal of 16 Hz, which means it corresponds to link 3. That means subject wants to communicate something to link 3. But what does the subject communicate? Only one message. Yes, link 3, now it is your turn to move by motor imagination and right hand motor imagination or left hand motor imagination and ERRP signal. I need to control your motion. So this could be done after few years of our understanding. Then we had in 2020, I mean, just, there are so many things we gap. In 2020, we developed another interesting things. The subject in the previous case has so much load. Why so much load? Because you see, the subject has to understand in which direction the robot has to move. This OPW plane carrying the robot arm has to cross OQW. So much load on the subject. And if the subject, he's having so much cognitive load and he's a neuromotor patient, should we load him so much? That is a big question. A question of ethics. We should not load a person who has already damaged brain or damaged neuromotor muscles. We should not load him so much. But how to do? We could not achieve those things earlier. So we loaded him. But now we have some more sophisticated thing in 2020. Let's see what. The subject's cognitive load or thinking process is minimum. He need not control the movement of the robot arm. He simply needs to specify where he wants to get. You can see there are different, bottles. There are different glasses filled with fruit juice of different colored fruit juice. You can imagine what could be the possible color, which is a pineapple, another thing, which is orange. You can easily understand. Okay. So the subject has a preference, for example, for the orange fruit juice, suppose. This is the robot arm. The robot arm will pick it up and feed it to the subject. But how does the subject specify that he wants to have only this orange juice, not the pineapple juice or something else? For this, there is a light emitting diode array, red light emitting diode array, which is flickering with 8 Hz. This light emitting diode array is by motor control, is moving over the plane, over this in this direction. It is moving. As it is moving, once it comes over the orange juice, that means this red light beam, which is flickering at 8 Hz, when it comes over this orange juice, The subject finds the red light beam is crossing 8 juice. He is simply concentrating on the orange juice. He did not do anything. He is simply looking at the orange juice. But as this red flickering light of 8 hertz crosses the orange juice, automatically subject will liberate 8 hertz signal as from SSBP, means from his occipital lobe. This 8 hertz signal is picked up by the EEG machine. And EEG machine understands now this is the position. 8 hertz means this red LED which is moving along the length of this. So that means row number 3 is the object position. So this BCI system decodes the row in row number 3 the glass is placed. But which column? 1, 2, 3, 3 column. Which column? That the machine cannot say right now. For this, again you have to do another cycle of SSBP. So there is a green LED light which is flickering at 12 hertz. This light beam is moving along Y direction, in this direction. As it sweeps over the orange juice, subject is simply looking at the orange juice. As it sweeps over the orange juice and the subject was observing the orange juice, so he will be liberating 12 hertz signal from his occipital lobe representing 12 hertz SSBP. The BCI system then decodes the signal and understands a 12 hertz SSBP, and that occurs. When did it occur? This occurred when the orange juice was being crossed by the red light. So it is recorded which time SSBP occurred when the orange juice is being traversed by green light. So the position of the green light is identified. Previously, position of the red light is identified. What does it mean? It means simply the XY coordinate of the orange juice. So the XY coordinate only needs to be specified to the BCI system. The rest of the thing the system can do autonomously. How? Because the subject mouth coordinate, if it is known, and the orange juice XY coordinate is known, the robot arm can pick up from here, and by automatic path planning and trajectory planning, it can bring the orange juice towards the mouth. So it is so simple by standard inverse kinematics technique of robotics. So only thing the subjective cognitive load is when the orange juice is being crossed first by red light beam. So X coordinate can be identified 3, and orange juice is being crossed by Y light beam, green light beam at first position, first column. So effectively row column position is determined and the robot arm can pick up the orange juice towards the subject's mouth. This was done in 2020. This work was published in one WCCI IEEE conference. This is the complete thing. But what is new? New is the scheme. But besides that, there are several local controller. The local controller means for each link, there is a local controller. You need to design the robot. So for robot can get the controller, how much is the movement of the robot, that is actually called sensory feedback to individual controller. And the robot can drive a motor driver to increase the current. So the sensory path is this way to robot, this way to robot, and the feedback signal is coming to motor driver to individual link. That is done for all the local controller. The robot computer simply needs to identify how much angle the individual link has to move. First link has to move by theta r, second by phi r, third at psi r. That is the reference angle the individual links has to move. The rest of the control task is done by the robot controller themselves. So we have a special type of two-loop robot controller that we design for very sophisticated robot controller, which can do automatically, and the subject need not be involved here. Subject needs to only specify the XY coordinate of the orange juice. So this was the robot controller basically. And so here we used two technique, sophistication. One is there are two loop, one inner loop, one outer loop. The benefit of this robot controller is there is a torque disturbance. In robotics, what happened when one link is connected with another, there are so many links, So all the links need to move simultaneously. Only the angles are specified. Angles are specified by inverse kinematics computing by the robot computer. So how much angle the individual link move to reach the target point, to reach the glass position. From the home position of the gripper, how much angle the robot individual link has to move to reach the target point. But to make it fast, all the link can move simultaneously. So theta, phi, psi can move simultaneously. So naturally, as all the links move, the moment of inertia of applied on individual motor, that changes. But you cannot keep track of that moment of inertia. There is no such method, no theory as such. Who will take care of the change of moment of inertia? Because so many links movement, if there is a 6-link robot arm, although I have shown 3-link robot arm, but in Jacko there is 6-link basically. So what to do? For this, you need to have more sophistication. What sophistication? That means you need to actually determine controller parameters. This is a controller. This is a fuzzy controller, Takagi-Sugeno fuzzy controller. You need to determine controller parameters K and L so that you need to apply the right torque for individual link. You generate the right torque for individual motor correctly so that overshoot is less. That means the target point is not being crossed by the robot. The settling time is faster. That means the robot can reach the target point quickly. And in order to achieve all these, you need to have a specific controller parameters. That means K and L are controller parameters, which is Takagi-Sugeno fuzzy controller, whose parameters are to be determined. And here we use one learning machine. One that is called learning automaton is singular, learning automata. This is basically a reward penalty type machine, whereby learning automata we can correctly design K and L, okay, for the Takagi-Sugeno type fuzzy controller. The rest of this thing is basically this is the motor broken into two components. One is the armature control part of the motor, and this is electrical side of the motor. Sorry, this is the mechanical side of the motor. So one mechanical, one is electrical part of the motor, and there is a torque disturbance which may occur when the glass is being picked up. Some water may come out from glass because of not properly holding the glass, or maybe torque disturbance because of other links movement simultaneously. So these are all torque disturbance. We can handle the torque disturbance by putting two loops. How by putting two loops? There is a good mathematics that I cannot show here because out of time, because we cannot finish it in time. It requires again 1 more hour to explain the mathematics. But how does the fuzzy logic work? That is one point. And how does this learning automaton work? That is another point. I just briefly outline. There are fuzzy rules like there are two input. One is error, positional error. That means actual desired position theta, and the feedback position theta c. The difference is called error, positional error, and derivative of error E dot t. There are rules like if error is suppose large and derivative of error is suppose small, then suppose armature voltage is something K1 into error plus L1 into error derivative. This K1, L1 or K2, L2, they are motor parameters. They are actually controller parameters which are determined by this learning automaton, which is more catchy part of our current research, which I will discuss in next slide. But in the current slide here, just I show how the Takagi-Sugeno controller works. See, these are the rules. Then you have to determine what is the membership of the error value with respect to the fuzzy set A1. I just discuss it in the next slide. And what is the membership of error dot value, DDT value under set B1. If we get these two things, then I just show in the next slide how it works and you can compute. Suppose this is the error is one rule is if error is small positive and error derivative, time derivative is small negative, then speed is K1 into error plus L1 into error dot. Just match similar rule. A1 and B1, they are actually explained like this. If error is small positive, error derivative is small negative, then speed is K1 into error plus L1 into error dot. This is one rule, suppose. The second rule, suppose if error is large positive and error dot is small negative, then speed is K2 into error plus L2 into error. This K1, L1, K2, L2 all are determined by learning automaton. That I'll show later. But right now, suppose this is the measurement, error equal to E dash. So once error is E dash by the fuzzy membership function of error is small positive, you got one value, membership value, say 0.7. Then suppose you have another membership function for error dot is small negative. See that this is error dash is negative, so it is small error dash is small negative curve. And error value is this much, error dash. So you got the membership value. Now these both thing has to connected by AND operator. So you take the joint operation by minimum of the value. Suppose it is 0.7, this is 0.3, so minimum is 0.3. This 0.3 is called firing strength of the rule. To what extent the rule is fired? It has a firing strength of 0.6. Now consider second rule. The measurement is same. See the same line, error dash and error dash same. For the same error dash and error dash derivative, these two are same aligned. So error dash is aligned here. So if error is large positive, this is large positive membership function. And error dash is small negative, this is error dash is small negative function, just previous. And this is the error dash value. So membership value of error to be large positive is this much. And membership value of error dot to be small negative is this much. Since there is the AND operator, we take joint occurrence, so minimum of these two value. Suppose it is 0.6, this is 0.4, so it is 0.4. Minimum is 0.4. Then what you do? You got firing strength here, and here firing strength, suppose it is 0.4, 0.3, and this is 0.4. So 0.3 into this thing. 0.3, so for each firing strength into this thing, K1 into error plus L1 into error dot you have to put. then plus firing strength of this rule into K2 into error plus L2 into error dot. That you have to do. So for each rule's output into corresponding firing strength, you are multiplying and add them up, divided by sum of the firing strength. This is actually the speed of the motor. So you get the speed of the motor, reference speed of the motor means here, that is the error EA. EA is proportional to speed of the motor. That way you can generate by Takagi-Sugeno fuzzy control. The next thing is basically how to determine that by learning automaton, as I told you, that we need to determine the KL values, which is most attractive part of this present research. That we do by some kind of reinforcement learning. And that one kind of reinforcement learning that we adopted is basically learning automaton. So what is done? Basically, I just show you, you need to prepare one table like this. Suppose this is error and error derivative. And there are basically possible, yes, over. Hello, I
sir,
can.
sorry to sir.
Oh,
Yes,
okay.
sir. Sir, really sorry to interrupt you, but
Okay,
this
I should
interruption
stop then.
just to 1 second, sir. This interruption is just to remind you that we are left with just another 10 minutes of this session,
No, I will finish
and
by
we have to
5
take
minutes. Okay.
questions.
Okay,
Okay, sir. Thank you, sir.
okay. So suppose
Really
this is
sorry for the
no
interruption.
problem. So this is suppose error and error derivative. Error can be small positive, error derivative can be small negative, as you found in the rule. Error is small positive, error derivative is small negative. In second rule, error is large positive, error derivative is small negative. That way we had the rule. So using the rule, we can get the small positive, suppose as a range like this for error, small negative of error dot, suppose as a range like this. In that way, for all rules, I have shown only for few rules, but there are so many rules in that way. Maybe say 1,000 rules like this. And for each case, we have all possible value of K1, L1, K2, L2, K3, L3, and so on. I have shown only for 5, but there will be approximately 100 such possible values or even more KIs, LIs. Now, how will you train this matrix? That is learning automation. How will you train this matrix? The idea is initially you choose the possible effective value of KIs, LIs such that in each row, the sum of these values must be 1. Suppose if there are 4 active rows, 4 active columns, the sum each will be 0.25. If there are, say, here also 4 active columns, so sum of them are 0.25. So this is 0 because this may not occur properly. This should not occur. In that way, suppose only 2 active columns, so they are 0.5 each. So that initialization of the M matrix. But then you have to change. How will you change? Suppose you found in the experimental trial, error became in this range and error derivative comes in the range. That means this rule is active. This blue colored rule is active. So then you found how to choose scale. You randomly choose any one. There are 4 possible values. Suppose you have chosen this thing, K2, L2. By choice of K2 being in this range and L2 in this range, randomly choose any values. And at the end, after several such experimental steps, when you found that because of choice of K2, L2, at the end of the iteration, when the error becomes very small and you stop, and the steady state error is very small below threshold, then you understand, yes, that choice of K2, L2 is good. Just like suppose you are playing football, for example, you are the person to kick the ball into the goal bar. You have done hundreds of experiments on different games, and you found if you just place yourself in that position and kick the ball that direction, then the goalkeeper will be befooled and he can kick the ball. So you remember this thing, and then you in your mind you understand those are my actually profiteering motives. So I can place myself, that will be getting rewards if I can place the ball rightly at that position, and you can kick forward. Similarly, so in the winning cases, if you remember, that has to be stored, winning cases or success cases, when steady state error is small, you can put it and you increase the probability. These are probability. You increase this probability by delta amount and decrease the probability of other case by delta by n. Suppose n is 3 here, such that sum of the probability remain 1. So if you repeat the experiment by several thousands and thousands of trials, it may require long time under offline condition, just in simulation, then entire matrix will come up with some values very big and some values small. Suppose ultimately you found that this value came to be 0.9 and other values are very, very small. What does it mean? In case error is small positive in the range and error dot is medium positive in the range, you choose this K2 and L2 because these gave you large value. So this is the idea that is called learning automaton we adopted in our system. We can analyze the choice of K2, these KL values, whether the system is stable by one method that we did by two methods, one by, in this case, root locus analysis of electrical engineering, or by basically by alternative technique by Lyapunov method. And this is our 2025 latest thing. This year we are going to publish this. Did not publish it yet. So basically, in this case, we instead of moving these lines, as you find over moving the beams, that takes a lot of time and motor control. We can avoid all this. Simply, we thought that this is the right choice. I mean, if we glow the beam here, there are some LEDs placed there. So LEDs are frequently, they are actually having frequency 8 hertz here. These two LEDs 12 hertz, these 12 shows 24 hertz, and you can then identify the row-wise move scanning of the LED's frequency here, and column-wise scanning of the frequency. You can determine the XY coordinate. The rest of the thing is just previous, and then we get very good results by doing that thing. Oh, so what are the benefits? Benefits is that we can handle dynamic loading by actually, because of torque management, as we did previously, torque management by handling this Takaji Shugeno fuzzy controller with KL setting by learning automaton. We can adjust the torque disturbance because of so many links movement of the robot simultaneously with the glass. And along with this, you have additional thing is cognitive load of the subject is minimum. He simply needs to specify the target point. He need not move. The movement will be done automatically by the robot. And we have a two-loop controller that reduces steady state error. So these are all the benefits. So this is all about, since time is out, I should have given some time for questioning. So let us stop here. This is all about, you can get the details, I mean, of the references. That is, most of our papers are all in IEEE transactions, and you can read it, you may ask questions later. So now if you have any question, please ask me. So it is over. Any questions you may ask right now? Yes, yes.
The participants, you may feel free to ask the questions about the session.
Yes, you may ask. You may not be nervous. You can ask anything. If I know it, I will be answering. If I do not know, I will say I do not know that, and we need to do experiment. If you have any question in mind, may be relevant, may not be relevant also, you may ask. I don't mind. Okay. No questions? Anybody can ask. I mean, nothing to be nervous. I mean, because in a very short time it is presented, so naturally understand getting the entire thing in a short time is really difficult. But still, if you have any question, it could be very simple question even, I don't mind. I will be answering.
Sir,
Yes.
someone is asking,
Yes.
if I'm not wrong, Abhijit Sarkar, is it
Mm-hmm.
possible to develop transfer-based or
Transfer
federated
learning.
learning automata?
Yes.
Yes,
Yes.
learning
Transfer
automata
learning.
that generalize across
Mm-hmm.
multiple users, devices,
Mm.
or modalities in large-scale BCI deployments.
Yes, yes, exactly. I mean, you can do transfer learning automata. It is possible. Okay, we did work on transfer learning and learning automation, but did not use transfer learning automation. Is it the question, I believe? That means you get knowledge from one domain problem and just use it in another BCI domain problem. That is also possible. In fact, we did work on transfer learning, but did not work on transfer learning automation. We did work on both transfer learning and learning automation separately. That is possible, and that will be very, very useful for, as he pointed out. Any other question?
Yes, sir, there is another question.
Yes.
Abhishek Banerjee is asking, can multi-model data fusion,
Mm-hmm.
EEG plus, EMG plus, EOG plus, eye tracking,
Mm-hmm.
strengthen MI and ERRP detection reliability?
Yes, yes. Actually, for ERRP detection, I mean, only brain signal is used, because ERRP, if you use by other modality, then it is not ERRP but error signal. That is possible. So you can use other modality, as you pointed out, and combine with EEG for error detection, as you said. But ERRP signal is only reserved for, actually that kind of signal only reserved for EEG. But other kind of similar signal representing possibility of error, of course, you can detect from other modality and fuse at whatever way you like say Dempster-Shafer theory, or say stochastic theory, or many, many algorithms are there. Yes, you are very right. That is possible, and that improves reliability of the system. Very good question. Anything else? Hello, are you connected?
Yes, sir.
Yes. Any more questions? If anybody asks, let them ask. Then one or two more questions. Then we can stop.
No more questions, sir. No one is asking any questions. And
Okay.
thank you all participants, and thank you, sir, for this enriching session. And thank you to take us to those uh, interesting and unknown avenues of neuromotor rehabilitation. Thank you once
Okay.
again.
Okay. So you can communicate this video to students, if they like, if they want it. Okay.
Yes, sir,
Or
definitely.
and if they want anything more, anything more about the write-up of this, I can also communicate to the chairperson, ma'am, and she can communicate to other. If you really want, if they want really. For examination of anything, if they want any kinds of write-up, I can send one PDF document carrying everything, of the entire thing and details. Okay?
Okay, sir.
If needed.
Thank you, sir.
Okay, thank
Good
you.
night.
Okay, thank you so much. Disconnect.